Log on, tune in, find out. Another good idea from Cambridge.
First lecture by Avi Wigderson on arithmetic complexity and the sum of square problem.
So I've just, well, as you heard from a friend, that apparently people were stuck somewhere and they are late, but I think we better start. Tell you about the plan of this. So Frank asked me to talk about this sum of squares problem. And somewhat, yeah, I didn't switch on the, oh, okay. So, want to talk about the sum of squares problem, but I thought that doesn't make much sense to talk about it without giving some background in arithmetic complexity. So there are going to be two talks, one today and the next one on Thursday afternoon. Today I'll just talk about some background in arithmetic complexity, but I'll just define this problem just so that you know what it is. Let me write some trivial identities. So x squared times y squared is x times y squared. I think everybody is happy with this. These are real numbers. Oops. Sorry. I hope I don't get it wrong, but I think it's x1, y1. Anybody can complete it. So this is turns out that you can write this product as a sum of 4 squares. And the general problem, the sum of squares problem, asks the question, what happens if you are trying to write sum of xi squared, sum of yi squared, let's say I goes from 1 to n.
There is a fifth one, yes?
Excuse me?
Fifth one. 1, 2, 1, 2, 4, 1, 2.
Yeah, 1, 2, 4.
Then 8.
Well, I will say more about this problem in general in just a second. So you want to write this as a sum of zi squared, zi bilinear, I goes from 1 to k. And of course this is always possible. I mean, if you expand it out, you get k, n squared terms. So the question is, what's the minimum k of n for which this is doable? This is a sum of squares problem, and believe it or not, it has to do with algebra, with topology, and with combinatorics. And this is a problem I'll explain more about the history and about the connection to arithmetic complexity next time. Okay, so let me start with the arithmetic complexity. Questions? Okay. Okay, good. So I want to talk about arithmetic complexity. And this is an extremely natural set of questions for, I think, any mathematician. And basically, you look at functions. I see some people of the late variety. You have some function, and you want to just know how complicated it is to compute it. And in fact, the functions we will be looking at are just polynomials, so the simplest functions there are. We'll just be looking at polynomials. And just ask how complex it is to compute them. So what's the model of computation? The model of computation will be simply if we have some polynomial over some field, to compute it, what we will do is just allow the operations that polynomials require, namely addition and multiplication. So what we will have is we'll write the variables at the bottom, and we'll allow to add them, multiply them, and also allow, beside the variables, also constants in the field. So we can multiply this, oops, maybe, and so on. So this is a model of computation. That's called a circuit, an arithmetic circuit. And when you compute with it, you just do the obvious operations, and eventually there is some function computed, and you would like it to be the polynomial you are interested in. So that's the computation by arithmetic circuit.
Doesn't allow division.
So we don't allow division. I'll mention division later, but let's not allow division. This is just addition, multiplication. You can have the constant as the inputs, or you can have them if you want. Let's say for addition gate, you can have instead of just plus of two things, just an arbitrary linear combination of two things. And this is, as I wrote it here, there's a fan-in two, just two inputs into every gate. And as I said, that's called the arithmetic circuit, and we denote these very two basic parameters for every polynomial. This is the size, and this is the depth of the smallest circuit for the smallest circuit and the shallowest circuit for computing the function. Size is, let's say, the number of edges, number of wires in the circuit, and this is the longest path. Okay. These definitions extend to, we'll start doing examples and you'll see. But the definition extends similarly to computing a set of polynomials, f1, f2, and similarly the depth. You just maybe want to, this will be f1, and here you'll compute f2 and so on. So you can have several outputs, and you can be interested in the time to, and the size and depth to compute a set of polynomials. When you're computing, just one more definition, when you are computing just one polynomial, another measure of complexity is L of f, which is a formula size. Formula size. What is a formula? A formula is a mathematical formula. It's the most normal, common thing we know about, which, if you think about it in these terms, is simply a tree. So it's something that just looks like, there are no things like this ever. So it's just a tree. And this can be plus and times and so on. That's a formula, and you may be interested in computing a polynomial by a formula. So that will be the formula side. Okay, so let's start doing examples and see what we can say about these interesting objects. So I'll talk just a little bit about computing polynomials in one variable, which seems like something we should understand completely, and you'll see how in general, this lecture will be about how pathetic our understanding is of this subject and how desperately we need your help. So, polynomials in one variable, it's really, so simple, right? So let's look at an example. Here's a polynomial in one variable, x to the d. Okay, raising a variable to the dth power. What is the size of this? How many operations, how many arithmetic operations? Yeah, it's about log d, because you can compute by your circuit, you can just compute x squared, x to the fourth, x to the whatever, something like 2 to the k, well, just k, 2 to the k, the first 2, which is bigger than d, and then multiply the appropriate subset to get the d you want. So this is at most 2 log d. That's good. So this we understand. This is a very special polynomial. You can take a random polynomial, some ai, x to the I goes, let's say, from 0 to d. What do you expect the complexity of such a polynomial would be in the worst case? The way it's written is, it takes a little more than d, because it seems like we have to maybe d log d, or something like this. But actually, there's a famous Horner rule that shows that you can actually do it in linear number of operations. That's not the point, it's an exercise. But in fact, for most, it's another, again, a very simple fact. For most, and you have to make sense of it over infinite fields like the complex numbers and so on, but you can argue that under any reasonable definition of for most polynomials over any field, polis f of degree d, this size just univariate, that is square root d. In fact, you can get something better, but anyway, there is an exponential gap between what most polynomials want and what very special polynomials want. Okay? So the question is, which are the easy polynomials? This is certainly easy. What are other easy polynomials? So here is a conjecture. The conjecture says that the following polynomial is not easy. So conjecture. So it's the greedy. Okay, so let's say that this is a polynomial. Then this is not logarithmic or polylogarithmic. Okay. This is very different than this one, because this one has just the same root many times, and this one has many different roots. Whether it's true or not, we don't know, but I'll leave you another exercise just to see. So you find this question interesting? Or anybody doesn't? It's okay. I mean, everybody has their set of, excuse me? So let me tell you about an implication of this conjecture. So some people.
What's known as an upper bound for that, by the way?
Excuse me?
What's known as an upper bound for that?
D.
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 So, and this lower bound of square root of d, is it right? I mean, is it?
You can get better. It really depends on the exact definition of a circuit. You can get something like d over log d. But anyway, you just want to point out there is an exponential gap there, right? So here's a consequence of this conjecture. If true, it implies that integer factoring the problem we so know and love and protects our internet acquisitions. So if this conjecture, if this conjecture is, very good, conjecture false implies that integer factoring has a polynomial size circuit. So it basically is in P. That's an exercise. Okay, questions so far? So I want to move to multivariate polynomials, and I have a lot to tell. So I did plan a full hour here, so I started late and I'll finish a little late. Okay. Yeah, it's sort of amazing that we don't have tools for understanding such a basic question, just univariate polynomials. But let's move to multivariate polynomials. So first I want to talk about just linear functions. So what do I mean by linear functions? I mean just computing matrix vector product. So fa of x is just a times x. So these are, if A is an n by n matrix, then this is really a family of functions, right? It's n functions, all the outputs of this matrix vector product. Okay, so what do we know about the complexity of such functions? It's again a counting argument. So again, I don't know if to call it a theorem or like. So it's a theorem, but sort of folklore. By the way, if I don't say what field I'm working on, so think that it's a complex number, so the real numbers. Although many of the things will work for every field, like the claim there and the claim here. For most matrices A, the complexity of F sub A is something like, well, it depends on the field, but over large fields it's n squared. So the best you can do is just compute the vector inner products one by one. So that's, and again, the question is, what are explicit hard matrices? So an open question, just to show you how much we don't know. Find an A such that something which cannot be computed in linear size. We don't know. We have no example, concrete example. We have lots of candidates, and we have no concrete example of a problem that we know that cannot be computed in linear size. Let me point out that for computing such functions over the reals or over the complex numbers, there is no need to multiply. Multiplications are not needed. They are just addition gates. It's just a circuit that just does linear combinations, right? A, the matrix is fixed, and we are just computing linear combinations, and we never need to compute more than linear combinations. So again, it seems like a really simple model, and we don't have a single example of an explicit matrix that cannot be done this way. We know that certain interesting matrices can be computed much faster than by n squared steps. For example, if we take the DFT matrix, the discrete Fourier transform matrix, so this is just a matrix that has omega to the ij in row I and column j. So omega is, let's say, an nth root of unity, this famous matrix. Then it's the famous fast Fourier transform algorithm that shows that this can be done in its most n log n steps. So I'm sure everybody knows Do you know who invented this algorithm? Gauss. Maybe also before Gauss, but certainly a written record. He needed to compute some orbits of some moons. And anyway, in his, you know, even without understanding German, you can see very well the algorithm in the text, the same recursive algorithm we know and love. Anyway, so this function can be solved in n-log n arithmetic operations very simply. And the question is whether it's tight. And if you think about this algorithm, the coefficients it is using, the kind of coefficients that go into the calculations are just roots of unity. That's the only coefficients used. It doesn't use, you know, 1 million in the computation or some strange or pi. It just uses roots of unity. But it turns out there is a beautiful result. I will not show you. I'll show you some proofs later, but it turns out that, so this is a theorem by Morgenstern. Theorem of Morgenstern, that the complexity of DFT, in fact, 1/2 here, which is exactly 1/2 here, and what is S star? So S star is that the circuit uses only small constants, uses only constants alpha of absolute value at most one. It's a beautiful proof, very elegant. If I have time at the end or you ask me, I'll show you. So that's a lower bound. Of course, it's not what we would like, because we would like this lower bound without any restriction. But at least we know this. And nobody is asking any questions or making any comments. Everything is clear. I'm always worried when this happens. Okay. So let me leave you just with one more open problem about this linear circuits, computing linear functions. Then we'll move to higher degree polynomials. But clearly, in all these questions, we lack methods. And for a restricted version of this question, further restricted version, Valiant had the method. So nobody could use it yet. But again, maybe you could. So I want to mention it. It's called the rigidity method. So assume that, okay, we cannot prove superlinear lower bound. So can we find a matrix for which you cannot compute this set of linear forms simultaneously in linear size and logarithmic depth, like the smallest possible thing? Even this we cannot rule out. So here is the theorem of Valiant. So first the definition. I won't put parameters, I'll just, so A is rigid if for, so A is a matrix, if for every sparse matrix S, and sparse I mean at most, let's say, n to the 1 plus epsilon non-zeros. So it's a matrix n by n, but it has very few non-zeros. If for every such matrix, the rank of A plus S, so you are allowed to perturb your matrix A by any set of sparse entries, and in any way there, okay? If the rank of A plus S is B, let's say. Okay? Let me put concrete. Okay, so let's call a matrix rigid if it satisfies this property. It's not only doesn't only have high rank, which is easy, but it cannot be, you cannot reduce the rank significantly to sublinear by changing just a little more than linear number of entries. So the theorem says that A is rigid, then S sub A has no circuit of size it's again beautiful proof, which I won't show you. All the things are pretty short and clever, but I won't show you this right now. So that's a method to get a lower bound. Just exhibit a rigid matrix or prove that Fourier transform matrix is rigid. I think everybody would feel that way. But we don't have methods to prove rigidity. It's somewhat one of these questions that mixes algebra and combinatorics, and I'm sure some people know that sometimes these questions are difficult. But anyway, I don't see a reason why we cannot prove this. But so far we don't. Okay, good. So let me questions so far. Okay, so I want to move to higher degree polynomials, and there are. Yes.
What about random matrix?
Yeah, I said most matrices are hard.
But they're rigid, right?
They are also rigid, yeah. Most matrices are rigid, yes. Thanks. They are rigid with very good parameters. You cannot reduce the rank this way by changing less than quadratic number of entries. Right, so they are rigid as can be. Okay, so I want to move to higher degree polynomials, and what interesting functions we have. We have, so if x and y are matrices, then for example, we may want to compute the product of two matrices, or we may want to compute a matrix to some high power like we did for a single variable. We want to compute the determinant of a matrix, and later we'll talk about the permanent of a matrix. I won't define it now, but I'm sure everybody knows what the permanent of a matrix is, but let me write it anyway. It's just like determinant without the sign, so the permanent n. Just like determinant without the sign. So, and there are some other polynomials that we'll mention later. Maybe I'll mention just one more. So the symmetric polynomial. We'll talk about all these guys. And D. This is a dissymmetric polynomial, and so on. You can be interested in lots and lots of these polynomials. Not only you may, I mean, people are. These are things that are being used in computation all the time. So if you have good algorithms for them, then you'll change the state of the art in lots of these programs, algebra programs, and lots of computations will be done much faster. So these questions are really basic and useful. So let me give you some examples of some things that can be done before we talk about the few lower bounds. We know some things that can be done faster than obvious. So what about how much does it take to compute the product of two matrices? How many operations? Yeah, so good. So everybody knows So the obvious thing is just to do all the inner products and n cube, but actually Strassen found that this obvious method is not the best one. So is there anyone in the room that has never seen this better algorithm? Good, thanks. So found a way to do it much faster. I'll tell you in a second what is the idea. He found a way that does it with much fewer operations than in cube. And then it was improved in a series of works, and the best is by Coppersmith and Winograd. It's got it to something like n to the 0.38. And as far as anybody knows, maybe it can be done in just quadratic time, which is the size of the input. So that would be really interesting. So what was Strassen's idea, and what goes on into all the other algorithms, just in a much more clever and much more sophisticated way? He said, well, let's look at n equals 2. So we want to compute the product of two matrices, x1, x2, x3, x4, y1, x2. And it seems like it requires 8 multiplications, at least if you do it the obvious way. But he found that this can be done. So the output here, which has these 4 bilinear forms, he showed that these 4 bilinear forms are spanned by 7 bilinear forms. Well, can be computed in short, spanned by bilinear forms requiring only 7 multiplications. So once you know it, it's not very difficult to find. You can try it, and you'll find these 7. You'll find how to generate using 7 multiplications things which span everything here. And this number is really log base 2 of 7. This exponent. So how does it come up? Once you know that you can do this, and in fact it's very important that you do this in a non-commutative regime, namely you are not allowed to replace xy by yx, then you just, if you have a big matrix times a big matrix, you just break it like this and recurse, do it recursively. So that's the source of this complexity. And it's true that these are 7 multiplications, and maybe the number of additions here is large, but it's completely swallowed in the recursion, and the linear number of the amount of linear work is always subsumed by the amount of nonlinear, by product case. So it's really the complexity. It's not just a multiplicative complexity. So you can do this faster. Okay, so let's look at something else. What's the complexity of determinant? Of n by n matrices. How many operations does it take to compute the determinant of a matrix? It's always like this in afternoon lectures. Is it polynomial, exponential, anything? Excuse me?
I'm going to stick my neck out as far as polynomial.
Polynomial, yes. What's a polynomial?
Square?
Well, It's not so difficult to see that if you could compute the determinant in some number of operations, you could multiply matrices in the same amount. So it should be harder than multiplying matrices. Well, what algorithm would you use? Doesn't matter what the complexity. What algorithm would you use? How do people compute determinants?
Row operation.
Yeah, so the row operation. So you do it by Gaussian elimination, right?
Or division.
Yeah, that's a very good thing. So forget it. I allow you division first of all. Suppose I allow you division, then you can do Gaussian elimination. What's the number of operations? Well, maybe you meant that there are n squared row operations, but each one is a linear, it's a row operation, so you have to do it. So this is at most n cubed with division. Actually, you can do it without divisions. I'll say something about this a little later. You don't have to have divisions. There are known algorithms that do it in this complexity without divisions. And in fact, the reason I'm not talking about divisions was early on observed by Strassen, who's really the father of this field, and most of the basic results are his, that in general, when you're computing polynomials, you don't need divisions. If you don't mind paying another factor of n, another factor of the degree, basically, of the polynomials you are computing, then you don't need division. So there is a general technique for eliminating division, as long as what you are computing does not have divisions. You're computing a polynomial. So you don't need divisions, and this can be done this way, but actually, in fact, there's a better thing that's known. It's roughly the same as computing a product of two matrices, maybe times log n. So you can actually bypass Gaussian elimination and just do it basically in the time it takes to multiply two matrices. Again, I'm not going to show you this, but I want to talk about, so we know that the determinant is polynomial. I should say that everybody believes, and the standard conjecture is that the size of the permanent, and we'll talk about it more on Thursday. Yeah, is, let's say, not polynomial. And I'll explain more about determinant and permanent next time, but I want to talk about the depth. So suppose you wanted to write a formula, or you wanted to write a circuit of shallow depth for determinant. So what is, it's almost the same question, the depth. Let me maybe say why it's the same question. It's very easy to see that if you have a formula, you can balance it. So the formula is a tree, and maybe the tree has long parts and short parts. But actually, whenever you have a tree, you can balance it by standard trick. So let me put here a comment, just a fact or an exercise, that the depth of f is at most log the formula size of f. So that's very simple to see. So asking these two questions is about the same question, right? So what do you think? What about, so if you are doing Gaussian elimination, or your favorite algorithm for, let's build the same favorite circuit for determinant, what is the depth of this circuit?
The obvious one seems to be n or something.
N, yeah. So the obvious one is n, because if you think about it, it's sort of a recursive algorithm, or a nested algorithm, and the obvious way will be about n. So the obvious thing here is n, and the obvious thing here is 2 to the n. So are there better formulas? Are there polynomial size formulas for determinant? It's a great question, and it's open. But the following is can be done. So it turns out that this is you can do much better. There is a sort of a parallel algorithm for determinant. You can compute the determinant in sort of a parallel way. And the first, this result was first proved by here field. And actually,
What is that? Sorry, what does that say at the top?
there is a formula for determinant.
I just can't read. No, I can't read
This, that's the name of the guy here field.
the actual bang.
The bound. There is a formula for the n by n determinant, which is whose size is n to the log n.
N to the log n.
Yeah, much better than 2 to the n. Okay, n to the log n. So just the exponent of this. And actually, this result is even better than stated because you can simultaneously compute the determinant by a shallow circuit of polynomial size. So there is actually not just a small formula, but actually there is a circuit of polynomial size and logarithmic depth. And that's the result of Berkowitz. And there are several algorithms, and I'll state a more general result in both of these. But I just want, if you haven't seen it, I just want to point out what's the source of this kind of result. It's not difficult at all if you realize some things about determinants. I assume everybody here knows that one of the authorities about determinants, a guy who wrote 2 books about determinants here in England, is who? Which famous author? No, nobody knows. He also wrote Alice in Wonderland. I'm serious. So I think people know he was a mathematician. He has 2 books on determinants. There are lots of wonderful identities about determinants, but basically there is one called the Samuelson identity, which relates. In fact, all these algorithms are based on doing something harder than determinants. They do the characteristic polynomial of these matrices, and when they do that, you can use various recursions. If you have a matrix, let's say A, which looks like this, let's say it has A here, some row R here, some column S here, and some submatrix here. So this is just one by one. You want to, let's say, P sub A is a characteristic polynomial. You want to express it in terms of the characteristic polynomial for M. It turns out that all you need to do is just matrix multiplication. So if you write this vector P here, so you know P, the coefficients, so this is, I don't know, P0, P1 are the coefficients here, P1, P0, P1, so P sub A, P whatever, N, and you want to do it from, let's call it Q0, Q1, Qn minus 1, where this is the coefficients of P sub n. So you just assume you recursively computed the characteristic polynomial of this guy. Want to compute the characteristic polynomial of this guy. So it's just some very simple matrix here, which has to be, I guess, n by n minus 1. So it looks like this. And here you start writing things that are related to this remaining information. So here it will be minus RS. Just this inner product of these two vectors. Here you'll have minus RMS. So this bilinear form. Here you'll have minus R m squared S, etc. So it will be a diagonal matrix. So all these things you can compute. These are matrix multiplication, matrix vector product. And you reduce by 1 via just this matrix multiplication. Maybe I should write wherever this may have been. Maybe it's 4 at this point, although it can be reduced. So you see, you can determinant A doesn't require division. There is no division here because you compute all the entries of the characteristic polynomial by multiplications, by linear operations. And you can see that it's very easy to see that the product of matrices it can be parallelized. So if you have a product of n matrices, you can compute just like we did with single variable. Over there, you can compute the powers. So in order to raise a matrix to the nth power, you just square it, fourth it, so on. So just log n matrix multiplications. And each one is depth log n because each, yeah, that's trivial. So that's where that's the source of the log n squared is.
About the
You
diagonal
might
of
find
zero.
the same matrix over and over again. Is that the point?
This m. What are you asking?
I can see, it looks now as though getting from PM to PA,
Yeah.
maybe that small depth, but how do you get?
Then you
Yes, I
continue. It will be a product of n matrices.
But why is that a power of a matrix? I can see why a power of a matrix is used as a not.
Also, yeah, so also the product of n matrices can be done in log n steps. But
Oh, yeah, sorry.
it's just the obvious recursive algorithm. Yeah. So it doesn't have to be a power. A product of n matrices, n by n matrices is just log n squared. Okay? Yeah. Okay, that's great. And actually, it turns out that this result here is much more general than the way it's written. So somehow we started with determinant that has a polynomial size circuit. And we saw that it actually has a polynomial size circuit which is shallow. First of all, I want to say this is something we don't expect to happen in general in Boolean circuits. And what we don't expect to happen in Boolean circuits happens here always. So if you have, so in some sense it's a generalization of this fact here. This is a theorem of Valiant, Kuhn, Berkowitz, and Rakov, which says that this is always possible. You can always take something that has small size, small arithmetic circuit, and convert it into another circuit which is both small and shallow. This is something we don't believe in. So in the Boolean world, it will be something like P equals NC, which we don't believe. And so the theorem says if f has, let's say, if f degree d, and S of f is S, then f has a circuit of size, something polynomial in S, I don't know, maybe this, and depth log S log Z. So you can reduce the depth to something like log squared. So of course this result implies this result. Right? All you assume is that it has small size, and you conclude that it has small size and small polylog depth. It would be great to talk about how this is proved, but I will not do it. I want to tell you the last 10 or 15 minutes about some lower bounds. Okay. Okay, so let's do some lower bounds. So how do you prove lower bound? So you can try the following idea. So now we can have several polynomials of high degree. So we can use the fact that we stated very early on, that's probably still there. For one variable, we know that this is, I mean, it's at most 2 log d, but it's at least log d. That's sort of obvious if you just want to. So maybe can say something about the following. Let's take n polynomials, x1 to the d, x2 to the d, xn to the d. So you just want to compute separately, raise each variable to the dth power. And the question is whether, I mean, these are distinct variables, so they don't mix. You know, take one variable, raise it to the dth power, second variable, raise it to the dth power, and so on. So maybe this should be n log d, and we take d equals n, for example, this will be a superlinear lower bound. What do you think? Sounds reasonable. So it seems that what's behind this kind of belief would be that, you know, whenever, what?
You cannot divide.
No. No. You cannot divide. It seems that what would stand behind this belief is what's called some kind of direct sum, which would say that if we have, you know, f1, f2, and so on, we want to compute a set of polynomials, and fi's have distinct variables. So they don't talk to each other. Every polynomial is in a different set of variables. So we would assume that this should be, well, or maybe equal the sum of the f of fi. Right? This, you know, if there's any justice in the world, then if polynomials don't have the same variables, then this should be true. So what do you think about this?
Why about x minus y times x plus y? Somehow.
It's not an example, they are the same.
It's
So
an example, but it
yeah.
just sort of somehow seems to suggest that you can produce things that maybe.
I don't know if this intuition, it's true that there are weird things happening in general, but I don't think that it's relevant to this question. But I claim that on the board, or at least that during the talk, on the board you had a counterexample to this.
I know that in case of matrices, if you want to do several matrix multiplications separately,
It's
then
very,
you can
not several matrix multiplications, several matrix vector products. So here is the counterexample which you have seen already. I claim two things that were written on the board. I claim that for most matrices A, S of Fa was something like n squared. So computing matrix vector products, so Fa of x, was, you know, A times x. I claim that was one fact you've seen. And the other fact you've seen was that, let me write it differently, AX, matrix multiplication, the complexity matrix, that's for any AN, was n to the 2.38 something, right? But what is this? This is A times the first vector, A times the second vector, A times the n vector. There are n functions here. They are on disjoint variables. These are just the columns of the matrix X. So this is completely wrong, completely wrong. I mean, there is a huge gap. I mean, the sum would be n cubed, but you can do it in almost quadratic time. So there is no direct sum, it's wrong. So certainly you cannot prove this by such a naive argument. But nevertheless, this is a theorem of Strassen again. It's a theorem of Strassen. So this I want to show you how it works. Okay, and very good. So then so let me just do a sketch. This already requires algebraic geometry. Just Bézout's theorem, but algebraic geometry. So what does Bézout tell us? That if we have a set of polynomials, g1, g2, etc., and we look at the set of all vectors x, let me write it like this. We have a set of polynomials g1, g2, gk, let's say, and the degrees g1, g2, gk are the degrees. Then the number of roots that are simultaneously satisfying all of them is at most the product of the di. Or infinity, but we will not be in this situation. Okay? It's Bézout's theorem. So how is it relevant to proving this fact? It's actually very simple. Here's a circuit, you know, with various operations, plus, sign. Here's what you can do. For every, so we want to create a set of polynomials that sort of allows us to use Bézout's theorem. So the idea would be the following: just label every vertex. Label every vertex with some letter, and just define the natural polynomials for every such label. So just give a polynomial to every vertex, namely the polynomial computed at this vertex. Okay, but think of it just for a second as the name of a variable. So these are new variables. You have the original variables, and you introduce lots of variables. How many variables? If the circuit had S, then we have x1 to xn are variables, and also gs are variables. Yeah. Okay, this circuit actually has many. It's supposed to compute x1 to the d, x2 to the d, xn to the d. That's what's it's supposed to do. So now write a bunch of polynomials. Whenever a particular gate computes, you know, is a product. In this case, we will have GB minus GU GW, because V is a product gate. But if this is the sum of, let's say, GA and GB, we write GU, or maybe alpha and beta, minus alpha GA minus beta GB. So for every gate, you write this equation that describes what the gate is doing. Okay, so just write these polynomials, and now so just have, and probably if it's an input, if this guy is just the input, you know, if we have some G, I don't know, C is just the input here, you just write GC minus Xi, this kind of polynomials. So we have this collection of polynomials, at most s of them, and we ask how many roots does this system have? How many roots does it have? Well, how many polynomials like this do we have? S. So we have at most s probably. What is the degrees? Degrees are just 1 or 2. In fact, the number of degree 2 are exactly the number of multiplication gates in this circuit. So there are at most 2 to the s roots. Right? That's most or infinity, but you'll see in a second. So we have an upper bound on the number of roots. Now let's prove a lower bound on the number of roots. It's very easy to prove a lower bound on the number of roots because we will add, I should have added to this system. So these are the final, the final gate. So I want to add, so this was some variable, I don't know. So for example, this was GL. So I will write here, I will also add GL minus 1 for every one of these output polynomials. Okay? So in particular, every root of this system satisfies xi to the d equals 1 for all I. Right? So every root of this system is actually, because the circuit computes these, computes x1 to the d, x2 to the d, and so on. Every one of these roots of unity, every one of these d to the n, so we have at least d to the n roots to this system of polynomials. And moreover, they are in one-to-one correspondence because once you set the values of the xi's, because the circuit is deterministic, you set out the values of all the gb's. So it's a finite number and it's at least this big. So we get that 2 to the s is greater than d to the n, and this lower bound n log d follows. Is it clear? So for those who, like Tim and some others maybe here who are interested in circuit lower bounds and in natural proofs and in progress measures on circuits and so on, you can see that this proof, even though I didn't present it this way, actually proves that the circuit must be large, must be complicated by a progress measure. What's the progress measure that says the progress measure on the arithmetic circuits is simply to every polynomial computed at any gate, you associate the degree of the variety satisfied by this type of polynomial equations below it. And this degree is a progress measure. It does not more than double at every step. It stays the same at a linear gate and it doubles at a multiplication gate at most. So it cannot grow too fast, and if you want to compute the variety of this degree, then you have to work hard. You have to work n log these steps. I want to just finish by telling you another result, even though I'll have no time to prove it, which is the following. And then I'll be done with an hour, even if I started late. So we have a nonlinear lower bound over there, Strassman's lower bound, but it's on computing a set of polynomials. Is there a lower bound we can prove on computing a single polynomial? And this beautiful theorem of Bauer and Strassen tells you that actually computing x1 to the d plus x2 to the d plus xn to the d log D. So computing them separately, we saw how it works. What about computing them, just their sum? Now we mix everything, and how can you prove something like this? You have to be really ingenious. So this follows from much, up to, some constant. What they prove is something much more shocking than this. What they prove is the following. Suppose that you can compute any polynomial f in S steps by a circuit of size S. Then you can compute all first partial derivatives of the circuit, not within a factor of n more, which is trivial, within some constant factor like 5. Okay. You can compute f itself also if you need to. And it's amazing, and their original proof used algebraic geometry and was quite complicated. But then the same Morgenstern I told you about before came up with something that, at least by picture, is a one-picture proof. And to elaborate it requires, I don't know, half a page of. So I'll draw the picture. And it's just remarkable. I assume you guys see how, you see why this implies, right? You see why this implies this, right? What are the partial derivatives of this polynomial? They are just, the separate powers of the xi, maybe d minus 1, but who cares, right? So you reduce the computation of one polynomial, proving a lower bound for the computation of one polynomial to lower bound the computation of many polynomials, and we've done that. I mean, that we know already. So it's just by reduction. Is this clear? So you don't need to do anything. So what's the picture? The picture is the following. This is Morgenstern picture. So this is what we assume, that we have some circuit that computed the polynomial f. And we want all partial derivatives. So let's look at again, look at the circuit, V, U, W. Various multiplication and the same polynomials computed at these points. What do we want? We want all partial derivatives of f. So let's start. So that's good. That's the mirror I have. Let's start with computed df with respect to itself. That's easy, right? I mean, that's just 1. And let's work our way up there by taking a mirror of this, that eventually will get us df dx. So we just take the mirror, so we just have df, to dx1, df dx. So that's what we want, and we want to do it, by a circuit. So what would make sense is that if we take a mirror, so here we'll have somehow df dgv, whatever it means. You have to define it. Actually, it's very natural, this definition. You can work it out. And so you work backwards and compute these things. And what's the key? The key is that suppose you computed everything up to some point, and you just want to compute another guy here. You are now on the way to the top. But it turns out just look at the chain rule, and you can see that you can compute this guy, which is df dgv dgu. You can compute this with the following information, this information, and this information. So somehow, just by the chain rule. It's a very simple exercise. So you just do it. So I guess that's enough for today. I had another lower bound to show you, but maybe I'll show it to you next time. Some exponential lower bound. Questions?
Those rules were not, I mean, those proofs were not really sensitive what kind of operations you did. So multiplication and
Really, they are very sensitive. Multiplication and addition are very. You mean to what?
you can divide also if you want.
You mean?
You can do some other operations, no?
Well, I mean, for the low bound here, we use Bezout. It talks about polynomials. So, what operation? So, what kind of
You
operations
can
do you have in
divide
mind?
if you want. No?
Divide is problematic. But as I said, you can eliminate division. Division is not, well, okay, within some factors. So, okay, I don't think we have a lower bound, superlinear lower bound when division is allowed. And I don't think this will work. At least I don't see an obvious way how it will work. For superpolynomial lower bound, we don't care if division is allowed or not because it can be eliminated. But yeah, it's a good question. I don't know what would happen with division. It would interfere also with this, but maybe there is some analog to this that allows division, I don't know. I should point out that this remarkable theorem, for example, another immediate consequence is that computing the inverse of a matrix is just as hard as computing the determinant, because the entries of the inverse are basically the first partial derivatives of the determinant. So it's another thing you get immediately. Yes?
So when you do matrix vector multiplication simultaneously, I think in your example at least the matrix is the same all the time, isn't it? Or
Well, what you do is...
But the question is that it's not an example for a system of things which are entirely disjoint.
Yes, it is, because you fix the matrix. You fix the first matrix to be a hard matrix.
Oh, those are constants.
Yes, you are allowed to use fast matrix multiplication even if one of the matrices is constant. So yeah, you fix one matrix to be a sort of random matrix.
I see, so those are not variables, those are constants.
On one matrix there are constants, in the
Good.
other there are variables.
Good.
Exactly, yes. Yes, I should have made it clear.
Thank you very much again.